Welcome to the presentation on designing distributed systems. In this session, we will explore the key principles, challenges, and the CAP theorem that drive the architecture of distributed systems. Let's dive in. Here's the agenda for today's presentation. First, we will look at the key principles and challenges of distributed systems. Then we will explore the CAP theorem, followed by strategies for designing distributed systems. We will also discuss the common challenges in distributed system design. Finally, we will summarize the key takeaways. Let's begin with the key principles of distributed systems. Decentralization. A distributed system does not rely on a single central authority, which makes it more resilient but introduces coordination challenges. Communication and coordination. Nodes in the system need reliable communication despite potential network issues like latency or message loss. Fault tolerance. Distributed systems need redundancy and failover mechanisms to ensure the system can recover from node failures. Scalability. To handle large volumes of users or data, distributed systems can scale both horizontally, adding more machines, and vertically, adding resources to existing machines. Distributed systems face a variety of challenges. Consistency issues. Maintaining synchronized data across distributed nodes can be complex, especially in real-time applications. Security concerns. Since data is spread across multiple nodes, securing the communication channels and protecting against unauthorized access becomes crucial. Latency and throughput. Ensuring low latency and high throughput across distributed systems, especially with large data, can be challenging. The network can often become a bottleneck. Now let's talk about the CAP theorem, which is a fundamental concept in distributed systems. According to this theorem, a distributed system can provide at most two of the three guarantees. C for consistency. Every read will return the most recent write. A for availability. Every request will get a response, even if it's not the latest data. P for partition tolerance. The system will continue functioning even if there is a network partition or communication failure. Understanding these trade-offs is crucial when designing a distributed system. Let's break down the trade-offs based on the CAP theorem. CP. Consistency plus partition tolerance. Systems like HBase or Zookeeper prioritize consistency and partition tolerance but may sacrifice availability during network partitions. CA. Consistency plus availability. This setup guarantees both consistency and availability, but it fails to handle network partitions, making it less feasible for distributed systems. AP. Availability plus partition tolerance. Systems like Cassandra or Couchbase prioritize availability and partition tolerance, but they may not always be fully consistent, often relying on eventual consistency. Designing distributed systems requires strategies to handle challenges like network failures and scaling. Replication and redundancy. By creating multiple copies of data across different nodes, we ensure availability even in the event of a failure. Consistency models. Depending on the needs of the system, we can either opt for eventual consistency or strong consistency. Consensus algorithms. Algorithms like Paxos and Raft are used to help nodes agree on decisions even if some nodes are unavailable. Data partitioning and sharding. Data is partitioned horizontally or vertically to scale the system and reduce bottlenecks. Load balancing. We use load balancers to distribute requests efficiently across multiple servers. In addition to the core design principles, there are several strategies that can help optimize distributed systems. Fault detection and recovery. Systems should be able to detect node failures quickly and recover from them without significant downtime. Eventual consistency. In some cases, it's acceptable to have temporary inconsistencies in data which can be resolved later. This is often used to improve system availability. Distributed transactions. Complex systems may require techniques like two-phase commit or saga pattern to ensure transactions across multiple nodes are consistent and reliable. When designing distributed systems, we also need to address the following challenges. Network partitioning. Communication failures between nodes can occur, so the system should be resilient and handle network partitions effectively. Eventual consistency. Managing temporary data inconsistency can be tricky, especially when handling conflicting updates. Distributed transactions. Coordinating transactions across different nodes introduces complexities in ensuring atomicity, consistency, and reliability. To summarize, designing distributed systems is a complex task that involves making trade-offs between consistency, availability, and partition tolerance, as defined by the CAP theorem. Key design considerations include fault tolerance, scalability, and consistency models. It's crucial to plan for network failures, replication, and load balancing to ensure the system performs efficiently and is resilient to failures. That concludes our presentation on designing distributed systems. I hope this has given you a clearer understanding of the principles, challenges, and design strategies. I will now open the floor to any questions you may have.